Now I'll make a brief concept-based review of relativity. Do you remember the two theories involved in relativity? First theory is the theory of special relativity, which was developed first by Albert Einstein. I spent most of my time covering special relativity because it's simpler than general relativity. General relativity was also developed by Albert Einstein, although a bit later. It is mathematically and intellectually more complex. They also have different domains. Special relativity deals with very small things on the atomic level, things like quantum physics, whereas general relativity deals with large things on the astronomical scale. Special relativity describes the structure and nature of space-time, whereas general relativity describes the theory of gravitation. Both of these theories were developed to cope with some failings of Newtonian mechanics at the extremes of the length and mass scales. At very, very small scales and tiny masses, Newtonian mechanics fails, which is where quantum mechanics and special relativity take over. General relativity, on the other hand, was developed to explain the failings of Newtonian mechanics on the largest end of the scale. Now let's recall the two main postulates of special relativity. First of all, we have the principle of relativity, which is quite aptly named. This principle states that the laws of physics are the same for all observers in uniform motion relative to one another. It's important to note that this does not include objects that are accelerating. Secondly, we have the uniformity of the speed of light. This postulate states that the speed of light is the same for all observers, regardless of their relative motion or of the motion of the light source. These two postulates of special relativity have many interesting and important implications. One that we mentioned was time dilation. Time dilation occurs when an object moving at a speed approaching the speed of light experiences time that is slower relative to that observed by a stationary observer. This means that the more quickly an object moves, the slower it experiences time. A second consequence is called length contraction. Length contraction is essentially the idea that objects are measured to be shortened in the direction that they are moving with respect to the observer. So, for example, a rocket traveling over the head of an observer will appear to be shortened in the direction it's traveling. A third consequence is relativistic mass. This means that an object appears to gain mass as it approaches the speed of light, meaning that it's harder to accelerate as you approach the speed of light. This prevents objects from exceeding the universal speed limit, which is the speed of light. This means that no object may move faster than the speed of light, making speed finite. A final consequence we discussed is the mass-energy equivalence principle, mathematically written as E equals mc squared. This principle states that rest mass is a type of energy.